So in today's video, we'll be looking at converting a stoichiometric table for continuous flow reactors. Now everything we'll be doing today will be just similar to what we did in our previous video. Just that for that one, because we're looking at batch reactors, we are considering amount of substance, which is the moles. And now because we are looking at flow reactors, we'll be considering flow rate instead of moles. So when you have a reaction, so let's say A plus B going into C plus D with your coefficient A, B, C, D. And let's assume A to be our limiting reagent. No, A is our limiting reagent. Now the conversion of A. So the conversion of A becomes the conversion of the whole process because now A is our limiting reagent. So conversion of A should be equal to the conversion of the whole process. And that should be equal to the initial flow rate of A minus the flow rate of A coming out all over the initial flow rate of A. So now this becomes a conversion for a continuous flow reactor. For batch reactors, we are looking at a moles, right? So that one you have something like Na0 minus Na all over Na0. Now because you are dealing with conversion, using the moles for the fluid actually wouldn't change anything like that. So let's consider something like this. We know that flow rate F is equal to the concentration times volume because the flow rate is in mole per second and then the concentration is in mole per meter cube. So if our volumetric flow rate is in meter cube per second, right, then we get this. So this is our volumetric flow rate. And when you are dealing with liquid phase reactions, from our previous video, we were able to establish the fact that for liquid phase reactions, it mostly occurs under constant volume. So our V is equal to our V0. So our volumetric flow rate will be equal to our initial volumetric flow rate. So we can substitute that here. So FA0 becomes CA0 times V0. And this is equal to CA0 V. So we can just substitute them here. So our conversion becomes CA0 V minus. So for FA, we get CA times V because V is constant. And then FA0 again gives us CA0 V. We can factorize V out to get CA0 minus CA. And then CA0 V. This cancels this. And then get our conversion to be CA0 minus CA all over CA0. So the conversion can still be written in the form of initial concentration minus the concentration outlet all over the initial concentration of the limiting reactant. Now when you come back to the stoichiometric table, it's very similar to what we did for the batch reactors. The only difference is that for the batch reactors, we're looking at moles, but then for continuous flow reactors, we are looking at the fluid. And then basically everything is the same thing. So for the species, when you are looking at this particular reaction, so let's say you have A, B, C, and D present, and let's say we have an innate species present. So the reactor feed, right? So the feed or initial amount, because we are looking at continuous flow reactors, our A for batch reactors we used Na0, right? But because you are looking at continuous flow reactors, we are going to look at the flow rate. So we are not going to look at moles. So A becomes FA0. That will be the initial flow rate of A entering the reactor. And that of B is supposed to be FB0. But then we establish something that FB0 can be written as. So just like the batch reactors, NB0 can be written as Na0 times theta B, where theta B is equal to NB0 over Na0, right? So we establish this fact. So the same thing applies. But here, because you're looking at fluid, our theta B will now be FB0 over FA0. So now this one becomes FA0 times theta B. And then our FC0 also becomes the same thing. So in a case where we have some of our products initially in the reactant, or initially in the feed. So our FC naught becomes FA naught multiplied by theta C, and then our FD naught also becomes FA naught multiplied by theta D, and our inert will also be Fi naught being equal to Fa naught theta I. And the next thing is we were looking at the change. Right? So the change is how much of A has been converted, how much of B has been converted. So we said that for reactants, if they are reactant, the change is negative because change is output minus input. And then for reactants, because there will be a conversion, the output will always be lesser than the input. So when you subtract them, you get negative, and that's the change we want. So the change we are evaluating here is output minus input. So for reactant, it's always negative, and then for product, they are positive. So just like how we saw for the batch reactors, so the change now becomes negative Fa naught times the conversion. Right? So how much of the initial has been converted. And then for the B, the same thing applies. Because now we are looking at the conversion. So A is a limiting reactant. Because A is a limiting reactant, the conversion is supposed to be for A, and I'm going to use that one throughout. So what you have to do is that you have to divide through by the coefficient of A, just like how we did for the batch reactors. So BB going into CC plus DD. So we divide through by A, and A, and then we get the ratio. Right? So the change of B now becomes negative Fa naught times the B over A, so this portion, right? B over A times the conversion, right? Or simply negative Fa naught B over A times the conversion, just like how we did for the batch reactors. So the batch reactors, you have something like negative Na naught B over Ax. So the same thing here. And then for C, because it's a product, it's going to be positive. So Fa naught C over A theta times the conversion. And then for D, Fa naught, so they are positives because they are product. D over A times conversion. And then for the inert, because the inert, what is entering will be the same as what is coming out. So the inert is 0, it has no change. Right? So inert means it doesn't take part in the reaction. And then for the last part, we want outlet or the reactor effluent. So the one coming out. So Fa naught will now give us Fe here because what is coming out to be Fa. And that's supposed to be Fa naught. So when you add the change to what is entering, we get what is coming out. Because you said the change is equal to output minus input. So if you want the output, you can just add the input to the change plus change, and that give us the output or the reactor outlet. So for A, you are going to get Fa naught plus this, but then this is negative, so minus Fa naught x. And when you factorize that, you are going to get Fa is equal to Fa naught out 1 minus x. And then for batch reactors, we had Na is equal to Na naught 1 minus x. So basically, this we are just replacing this with Fa naught. We are just going to write the same thing. Fb now becomes Fa naught bracket open theta b minus b over ax. For Fc, we are going to get, because we are adding, so Fa naught out, you can get theta c plus c over ax. And then for Fd, it's equal to Fa naught theta d plus d over ax. And then for the inert, it will still be the same, Fa naught theta I. And then we found the total. So just like everything is similar to the batch reactor. So we found the total moles at the outlet. So the total moles at the outlet. For this, we're looking at the total fluid at the outlet, and that would be summation of all this. So when you sum everything, I'm going to get F T naught plus sigma F A naught X. So if you want to understand this, you can go and watch the previous video. So we were able to establish this. Right? And then for the batch reactor sort, it was N T naught plus sigma N A naught X, which is basically the same thing. So we are replacing this with flow rates. So we come to the conclusion that we establish the fact that our sigma here is equal to the summation of all the stoichiometric coefficients. So C over A plus D over A minus B over A. So we are just adding the products minus the reactants. So A coefficient is 1, so minus 1. And that is for the sigma. Yes, so we establish everything here. So now the only thing we are supposed to know is that for continuous flow reactors, the approach for the stoichiometric table and the conversion is similar to the batch reactors, just that we are considering flow rates for the continuous flow reactors, and then for batch reactors, we are looking at the number of moles. So that's the only difference. So for liquid phase reactions too, the same assumption still holds. V is equal to V naught. And for gas phase reactions, we establish the fact that V is equal to 1 plus epsilon x V naught times. So we'll be able to establish that this is actually the general expression times T naught over T multiplying P naught over P. So we are able to establish this. And we said that for isothermal, so this is actually the general expression for gas phase reactions or reactions where the volume is not constant. So in such a reaction, if you are dealing with isothermal means the temperatures are the same, right? So the initial and the final temperatures are the same. So this part goes to 1. And then we are left it V is equal to 1 plus epsilon x V naught P naught over P. And then if there is no pressure drop, that means the pressure is constant. Then this also goes to 1, and we are left it this portion alone. So in a situation where we are looking at a reaction which is occurring under isothermal and isobaric, then we will say that our V is equal to 1 plus epsilon x V naught. X is our conversion, right? And our epsilon, we said our epsilon is equal to the mole fraction of the limiting reactant, so the initial mole fraction times sigma, right? And then we know sigma from this. We're able to, I think I established sigma from this. Yes, so now we know this, and then we can find this. So if the field is entering at pure A, that means the mole fraction of A is 1. We can find sigma 2, and then that can help us to find this. When a question doesn't talk about isothermal or any pressure drop, then I'm going to use this to find your volume V. The essence of this volume V is that when I limit the gas phase reactions, because V is not equal to V naught, when you want to find your FA will be CA times V, and you need to find this V. When you want to find your FE naught, your FE naught will be CA naught times V naught. So if you've been given V naught, you can just find it straight away. But then for liquid phase reactions, your V is equal to V naught. So your FA becomes CA times V or CA times V naught. And then your FA naught also becomes CA naught times V naught or times V. So any of them works. And then for gas phase reactions, your V is not equal to your V naught. And this V here is volumetric fluids, not volume. Yes, so that will be all for now. So this part is P over P naught rather. Yes, so the pressure over the initial pressure. So this becomes the general equation. V is equal to 1 plus epsilon x v naught t naught over t times p over p naught. So for isothermal reactions, this part goes to 1. For isothermal and adiabatic, this part goes to 1. And we are left with this. For isobaric process, this part goes to 1. And we are left with t naught over t. So now only this part works. Yes, so that will be all for now.